Hey everybody, this is Larry. This is Leetcode Contest 194 weekly. You're already seeing the results, um, so I'm actually trying something new for this video, which is that I'm gonna have the explanation first, and then you could watch the live Larry solving it and struggling, particularly on this contest afterwards. Let me know how you feel about this format. Is it better? Is it worse? I don't know. I'm playing around with it. Hit the like button, hit the subscribe button, join the Discord, and here we go. Whew, okay, well, yeah, let's go over the contest now. So I finished at 115, which is kind of okay, considering that I really struggled on Q4, even though it was, in retrospect, if I was more practiced, I could have gotten it, but I just haven't done, I just don't remember, I just had trouble remember how to do back edges, so that took a while. But okay, if you didn't know what that means, that's okay. Let's get started and review the solutions and explanations. Okay. XOR operation in an array. Given an integer n and an integer start, define an array nums where num sub I is equal to start plus 2 times I so index. So yeah, so this one the hard part is just converting the numbers from an index I, do I put y, into this formula they tell you, and then XOR everything together. That's pretty much it for this one. It's linear time. I don't even know if I recommend it. I mean, this is a for loop. I don't know if I recommend it for an interview, but you should be able to get this pretty quickly, hopefully. Yeah. Q2, making file names unique. So this one, the tricky part is that there are a couple of edge cases, and the second trickiest part is that the n is 5 times 10 to the 4th. And what that means is that you cannot do a quadratic time algorithm, meaning no n square. You have to do an O of n or n log n, depending on what language you're in, and that's it. So the idea, and I actually got this wrong the first time, but the idea is that you first, yeah, if you look at the name, and if the name you haven't seen it before, then it's good. And then you keep track of if you use it again, you have to watch it again, right? And then later, if you do see the name, then you look at the counter that it was previously incremented by 1, so that the next time you see the name, it will be +1, and then you just keep on looking that way, and that's pretty much it, really. You just increment it, and then just check to see if it's in it. If it's not, then I think this should always be okay. Otherwise, you just add a few times. But this already makes it this in theory could still be n square ish, but it's fast enough. Yeah. So that's Q2, but just keeping track of the previous one, and here we can actually and we should keep track of the previous one as well. But yeah, actually, I don't know why I did it this way, because I think I just kind of did it weirdly. So how I would do it again is that if this is the case, then I would do counter is you go to previous name, and then just do something like the same thing as before. Yeah, and then previous +1, and then just keep going, right? So if you do something like that, you get down to linear time. The space is also going to be linear because you have one entry in the previous for each string, and that's pretty much it. It's pretty hard for Q2, but on an interview problem, this is probably a little bit harder than I would expect, only because maybe in 45 minutes it's okay, but it's still a little bit harder than I would expect. In competitive, I guess it's okay. It is what it is. Yeah, and especially for this contest, I thought that this was as contest-y as it goes. But yeah. Okay, Q3. Avoid floods in the city. So this one was a hard problem. Let's saying that, and there might be other different ways to solve it. If you watch it to the end, I'm probably going to do code reviews of other people's solutions, so then we can maybe learn other techniques. But my technique here is that the thing to notice is, and I actually, when I was solving this live, as you may recall. I actually tried to do some stack stuff, and then I like greedy and stack. But the problem with greedy is that it's not always right. In this case, n is 10 to the 5th, so you definitely cannot do anything slower than n log n. So n squared is out of the question. So what I did was noticing that, so basically each step of the way we look at each number at a time. So let's say we put in 1. Okay, that's good. We know that we have to so given that 1 I'm trying to think about a way to explain it in a way that you can also learn from, but it's a little bit tricky because what I did, to be honest, and you could watch it, the live portion of this video, which is that I just tried a few things and then got a few things wrong, and then mentally tried this until it worked. It's not the ideal way to think about some problems sometimes, but sometimes you have to grind, and when you grind and you get it, it still feels good, even if you get a lot of wrong answers like I did, because I tried two different greedy algorithms and it was a little bit off. But the less greedy algorithm though, it's that so let's say you put in a 1, so now there are a couple of logical statements, right? If you put in a 1, you're like, okay, let's see if in the future we have another 1. If there is, then we have to remember to clear the 1 before the next one. Same thing for 2. So in English, I think that makes sense, and that's basically my greedy algorithm. And if you cannot do that, then you return, the empty array for not able to do that. So of course, in this case, the implementation is tricky, right? Because if you do it naively, then it's just going to be, okay, let's look at a 1, and then let's look at find the next one. And that's going to be all of n squared. As we said, that's too slow. So what I did was I actually implemented it with a heap. First of all, it's kind of tricky, even though it's only 25 lines of code. So definitely take your time and stuff like that. But the idea is that for each, so first we do a pre-processing step, so that for each lookup, for each number, we just basically put it into that numbers with mapping a number to the index to an array. So now, for example, 1. So after one loop, for example, okay, let's just go to this case because that was the one I had trouble with anyway. So after one loop, actually we could visualize it by running it, right? So hope this helps. But basically, okay, well, it helped a little bit. But basically, 1 is in position 0 and 5. 0, okay, 0 is a little bit off because I forgot to take off 0. Okay, but 2, for example, is in position 2 and 6. 3 is in position 3, right? Okay, so that sets up the heap. And now we set up, and then now we go through again from left to right. So we go, okay, let's look at, now that we look at 1, we put it, if there's a 1 left in the rest of the array, that means we have to clear 1 in the future. We'll put it in. And what I did was I put everything in a priority heap, or priority queue, which is a heap. So for 1, I put in 1 with an index of 6, or I think it was 6, right? Or maybe 5. Yeah, sorry, index of 5, right? So now after one loop, the heap will contain, the index 5, and just tracking that as a 1. And then at 0, it just tries to remove anything that it needs to do, right? Because you know that you need to do. And then here, it just clears up to 1. And then 2, same thing. It goes to, I think, 6 now in 2. And then at 3, we don't put on the heap because we don't have to clear the 3. We don't see it later on. And so then like the 3, you could just pretty much ignore it. And then for 0, now you remove the heap again, and then that's good. And then now by the time we do 1, we know that it's clear, and we keep a set to make sure that that's the case by adding and removing as we go on. and same thing for 2. I think there was another case that illustrates the other case where, yeah, here, for example, I mean, there's some variation on this one, but basically, the key note is that, yeah, given that 1 and 2, then we know that, 0, 1, 2, 3, 4. So there's a 4, and then there's a 5, 1. And in this heap, or priority queue, we put the 4 in front because that comes in earlier. So the idea is that we always take the item that is the earliest that we need, and then queue it on the next possible spot, which is next 0. So that's kind of the algorithm I have. What's the complexity? So the complexity is n log n. This is O of n because each item is going to be appended to the lookup at most once. This assumes that, of course, hash tables are or dictionaries are all of one lookup. You could do your own math otherwise. I know that, you know, there's collusion and stuff like that, but let's just say it's all of 1, right? And then for addition, this does because we use a deck, so we could remove from the beginning. So this is all of, well, each item can only be removed once, so this is in total O of n, where this is at most log n, given n of these, so this is O of n log n. In the else statement, we only pop each element once, so it's also O of n log n here, so O of n log n total. The space is going to be O of n for the heap and the dictionary. So O of n log n time, O of n space, and that's how I solve this problem. I did it a couple of times and it was hard, so don't feel so bad. But yeah, this is pretty hard for an interview and probably relatively hard for competitive programming, or at least in Leetcode competitive programming, to be honest, because I expect it to be easier, to be honest. But anyway, that's all I have for this problem. Let's see Q4. Yeah, that's all I have for this problem. Find critical and pseudo-critical edges in minimum spanning tree. Okay, so what is there to say about this one? This one was hard. So in the contest, only 121 people solved it. So you know that, yeah, this is a pretty hard problem, and people didn't even bother submitting it. So this is definitely a very hard problem. I was able to get it at the very last minute with a lot of code. I wrote 105 lines of code, but a lot of it is that I was a little bit out of practice, so you could definitely clean this up. And I was just trying to get it at the end because I solved this with about 5 minutes to go in the contest. So I just wanted to, you know, like it was a freebie. If I didn't get it, I didn't get it, right? So yeah. So the idea is that we call from, and a lot of this, it took me a long time to prove. And I have, like, if you look at the live solving of this, a lot of it is just me doing nothing, it seems like. I was just thinking about it, and basically, if you could see this, I have a notebook that I bring out for competitive programming, but it actually doesn't come up very often for Leetcode, but this time I needed it. So, and I was just drawing little things to drawing edges and trees to kind of figure it out. One key thing to note before we start is knowing that n is less than 100. And when n is less than 100, and also the other one is weights is less than 1,000. So what that means is that, and that this part actually doesn't matter that much, to be honest. Maybe, because they only have most 200 edges anyway. But it just makes certain things a lot easier. But basically, given that n is 100, we can do things more liberally. So my idea was, so basically, okay, let's go over some observations first. The first observation is noting that using Cusco's algorithm, or I think it's Cusco, is the, now Prim is the other one, but using Cusco's algorithm, and hope I said the name right, I haven't said it in a long time, but basically it's a minimum spanning tree algorithm, and there's a lot of computer science algorithmic fundamentals in this problem, so it's hard. But the idea is that, you know, one at a time, and this is the part where I wish I had a pen thingy, but but you just but it's a little bit almost like so it's greedy. Costco algorithm is greedy, and the observation is that for Costco, you always want to insert the same weighted edges at roughly the same time. I mean, if you just need any minimum spanning tree for the Costco's algorithm, then it doesn't actually matter what ordering it is. But for this problem, we're trying to get a critical edge, and a critical edge is such an edge that when you remove it, it increases the minimum spanning tree, right? Which is another way of saying it. I don't think it said it this. Oh, actually, no, it does say it this way. But I think I didn't understand it. But so basically, we go one by one. Given that the rates goes from 1 to 1,000, what I did was that I wrote a for loop. I use union find for this, and then if it's done, we set it to done afterwards, meaning that if we have more than one component, then it's done. If we have only one component, that means we have a minimum spanning tree and it's done, right? Otherwise, I keep track of all the edges that we added or we used this round, which is all the edges of the same weight. Basically what I did was, and this is really hard to explain, but basically what I did was I constructed a new graph that consists of only the parent. So basically the nodes that are the nodes that combine to make the new graph. So basically, if for example, at a very basic case, let's say you have a 1 is equal to 2, 2 is a node, 3 connected to 4, and now we're trying to process and then maybe connected to 5, say. And then now we're trying to process 1 to 4 as an edge and 2 to 5 as an edge, right? And but because that we combine these into one super node, let's say super 1, and this is super 2. So now we have edges that goes from super 1 to super 2, right? And in fact, we have 2 of these. And that'll come into play later. But basically, that's just the idea of combining nodes as part of the Costco's algorithm. And then on each last processing, you look at the edge that allows you to, and then you just process them together, because basically, at the end of processing an edge weight, you always have the same components. So that's the part that I had to prove for a little bit while. And by drawing a lot of diagrams, but basically that is the case because you can prove that if you had another case that later, then you could always just choose that edge now. So that I know it's a little bit hand wavy. Definitely try to prove it at home. It's a little tricky. So basically after that, now I try to find the cycles, and what that means is that if there's a cycle, then every edge in that cycle is not necessary because you only need a subset of them, right? So basically, for example, the really basic idea is like the triangle, right? Like 1 is connected to 2 is connected to 3, and then 1 is connected to 3. So you have a triangle. You have a triangle, and then you only need 2 of those 3 edges, right? So that's basically, and when you have a cycle, that means that any of those 3 edges are not necessary because you can remove one of them and then it'll still be fine. So that's what a cycle means for a minimum spanning tree, because if you have a cycle, you remove one edge, you will get a tree, right? So that's kind of how we structure it. And then the key thing to note is that it doesn't have to be a cycle starting from the beginning, right? You can imagine that there's an additional edge from 1 to 4, so it looks like a triangle with a little string dangling on top. And in that case, the 1 to 4 is critical, right? So that's what I did with the cycle, though I got confused and did it backwards. But that's pretty much it. I did a lot of algorithms. The rest of that is the implementation detail, but that's kind of the idea, and it took me a little while to get that quite right, because I just had off by ones and stuff like that, because I haven't implemented cycle counting in a long time. And also this is, for me, the way that I implement it is, as we kind of notice, there's actually, there are duplicate edges in these supergraphs, right? Because in the beginning, because when you combine these nodes, at least this is the way that I did it. When you combine the nodes, you have these super edges, right? And then these super edges can have duplicate edges. So the standard way that I would have done a DFS, where you keep track of the parent, is not good enough. You actually could do it with a parent edge, because now if you have multiple edges going to the same node, then by definition you could loop back, right? So yeah, implementation is a little tricky, but I just do a depth first search. Yeah, so let's go over implementation a little bit. So I hope I explained the theory part of it. But the implementation, I use union find to look at the edges. Where is this? Oh, so for each weight, which we reprocessed already into where did I reprocess this? Oh yeah, we process each edge. So you could think of it as sorting it by the weights and then putting them together, and then we process them all at the same time. We do a union find. If this is a tree, we're done, but we still have to do some calculations. So we're done. We return the edges that we must have, and then edges that we maybe need. So basically, I construct a supergraph by using the parent index as the identifier for the supernode, and then I just look at, well, I get the cycle, and we'll go over the cycle next. But just assume that the cycle does what it does, and then it puts all the edges that you need in there, or you don't need, maybe. Yeah, you don't need in there. No, you put all the edges that you need in there as part of it. I think I did this the other way by accident. That's why. Anyway, I'll go over why in a second, because I was thinking about critical edges, so that actually makes sense now that I think about it. But yeah, and then after we get all the cycles and put in all the edges that are good and consider, we go again. Basically, this is just, actually I could have probably just looked for UW now that I look at this, but again I had a couple minutes left, so I rushed it. But basically, yeah, we just put it, if it's in the things that we are in it, then we put in must. If it is not in it, then we put it in maybe. And then after that we just update the graph with the union find. So the get cycle part is a little tricky. As I said, I use the parent edge instead of parent, but the rest of this is basically finding a critical edge, which is that's the strategy that I took. But basically the idea is keeping track of the minimum time and of when you visited a node, and then for each node, see if that this is a lot of math, but slash algorithms. But basically, for each tree or each DFS tree, if there's a back edge, you mark that as being earlier, and then you mark that current edge as a back edge. Otherwise, if you're not able to go back, then you consider it as a critical edge. And if it's a critical edge, that means that this edge, there's no way to be a cycle from this edge, so you put it into the must list for me. I know that's a little bit hand-wavy, it's a little bit tricky. Leave a comment in the YouTube video. Let me know your confusion, and also join the Discord channel, and I'll be happy to explain it a little bit further depending on your confusion. There's a lot of math in this one, so it's hard for me to figure out like what level to kind of talk about it. Maybe I'll do another video in the future to kind of now that I recollect all the basic feedbacks, because the things you need to know about this problem is minimum spanning tree, Kuskov algorithm, greedy part of the Kuskov algorithm so that you could prove certain things, and then critical path / DFS / back edges, right? So these are like 3.5 things maybe that you need to know. 3.5, 4-ish things. So it's a really hard problem. I would not feel that bad if you don't get it immediately. And also this video may not be enough because it's hard to explain all 4 of those things from first principles. But that's how I did this problem. Whew, that was tiring just even explaining it. But okay. I think now, because this is the end of the contest, let me refresh. What I like to do is do a code review so I could see what I can learn, especially for this problem set. There's gonna be a lot to learn. Okay, Q1 is oh yeah, that's the XOR. People did it really fast. Wow, 30 seconds. Well done. I think I was just loading too slowly. Maybe that's my excuse and I'm sticking to it. Okay, so I don't need to review that one. Q2. Okay, so that's the lookup one. Use unordered map, bold move. But okay, basically same-ish algorithm as I did. Though I forgot to increment the count, so mine is actually a little bit slower. I'm glad that it passed, but that was a little bit of luck. Okay. This is very intense way of converting it from into a string, but okay. So same algorithm, looks the same. Yeah. Okay. Okay. A lot of us had wrong answers probably from the time limit exceeded as well. This looks really close to my code, and I mean that respectfully. I wish I wrote it that quick, but yeah, they took 10 minutes maybe. But Q4 was very good for them. Okay, let's do Q3. Which one's Q3? Q3 is the void flood. I used the heap. I think this is maybe unique for me, so let's take a look. Okay, well, actually, they did the same thing, I think, with a priority queue. That's beautiful. Except for that they did it way faster. That's not 7 minutes as opposed to 22 minutes. That's why they're so good. And also advertising Microsoft. Gotta represent, I suppose. Alex is not in this round, so because it would be good to. What is going? Okay, let's just move on. Okay. Basically, it's what's F? Oh, okay. H is equal to space dot. Oh, I see. I guess. I'm not sure I understand that one, to be honest. Kind of, maybe. I get the idea what they're going for, but I think I'm missing some intuition here. There's some beautiful ASCII art that we're going to skip. I think this uses the same technique that they did, but so if this is greater than 0, we have to set -1, and then we put stuff. What is OR? I see. So it's just looking backwards. That's an interesting way to do it. So the idea is that if you get a 0, you so it's parsing it one by one, but if you get a 0, you put that index in there, and then otherwise you greedily. Okay, I see it. So basically, what this problem is doing is that it's the other way, right? So you have a 1, you put everything that you that is not clear into a set or with the table or yeah, with a set, and then it and then you kind of keep track of the last 0 or the first zeros that you have available to you, and then when you see a number that you already seen before, you go back and you clear it for that number. Actually, that's pretty clever, and yeah, okay, that makes sense. So you use a yeah, okay. I mean, that makes sense to me. Okay. I don't know if I could come up with it though, but I might have to think about it some more. But yeah, got it way faster than I did. But I mean, these are kind of roughly. I mean, I had 2 wrong answers, but and a little bit slow. But like I'm on par with maybe top 50 at this point. But I was just really slow on the last one. Okay, let's see if there's a. Maybe people are just really good in the last one, and that's possible because for the last one it feels so they sort by edges and then they merge them. I mean, this merge is just union fine, right? Just want to make sure. Yep. This also is union fine, and then just and fine. I guess this is the same way. And okay, this is a lot of scrolling. 15 minutes. Wow. Mad props to that. Everyone has a lot of code, so I don't think. At least I don't feel bad knowing that my algorithm is roughly right. I mean, it's submitted, so it's good, but it's not too off. Everyone's doing union fine as well. It's just that, huh? Wait, this one? Oh no, no, this is because this one doesn't have. How do you? This is way easier than the way that I did it for finding a critical path. And I'm not quite sure why that is. Well, they do it an edge at a time. Oh, no, they don't. They do it all together. Oh, I see. Oh, huh. I didn't know. I didn't think that was fast enough. So basically, what they did was, okay. So I guess my algorithm is faster than this one. But basically, what they did was that for each edge, just construct the cusco again, or well, for each edge, see if that for each edge, see if you need it by processing the rest of the set. So okay, I didn't know that was fast enough. If that was fast enough, I would have so done it this way. But yeah, but the idea is that basically it's just instead of doing the cycle thing that I did with crazy math, not crazy math, but like it's just layered. What they did was that, given a cycle, I mean, it's essentially saying the same thing, but they did it more naively, which is that we remove an edge. Let's say we remove this edge and see if it's still connected. If it is, then they're good. Otherwise, wow. I didn't know. So that takes all of 200 times 100 times 100. I guess that makes sense. I did it a little bit slower, so if I did 1,000 times 100, that's why. I don't think I could do 1,000 times 100 times 100. That's 5 times slower. Okay, well, I learned something today. I think it seems like most of the algorithms are doing the same thing, and also they did in C++, um, so that makes it easier. Yeah, okay. I think the thing is that in C++ maybe you could get away with it. I don't think I could get it away with it with Python. I could be wrong on that one, but because basically that's what they did here as well. So that feels a little bad because that was the hard part of how I solved it was that, and I thought that that would be too slow. But yeah, okay. Well, anyway, finished 115, which is okay. Maybe that's why everyone did. I thought that was. Huh, that feels a little bad, but because it seems like other people did it that way as well. But yeah, okay. That's why for this contest, I guess I didn't do that. I did okay. Yeah, if you like this, hit the like button, hit the subscribe button, and let me know what you think. I will see you next week or whatever. Bye bye. Hey everybody, this is Larry. This is Leetcode Weekly Contest 194. Uh, wish me good luck. Usually need it. Has been a little bit bad lately, so I'm gonna maybe slow down and just try to get it right and not rush it. Yeah, about 15 seconds to go. Hit the like button, hit the subscribe button, join the Discord. Leave me notes on the contest on the comments. How did you do? Which one was your favorite problem? Which one did you have trouble with? Let me know. All right, let's get started. And here we go. Come on, loading. Q1, XOR operations in an array. So for this problem, it was pretty much implement what they tell you to do, which is for each index, you map it to this other in formula, and then you XOR each number. That's pretty straightforward. And if it sounds straightforward, it's because that's pretty much all I had to do. Yeah. And watch me do this, I suppose. Yep. Q2, making file names unique. Given an array of string names. Oh, this one. Yeah, so this one, to be honest, I looked at it. I was like, okay, that looks straightforward. I made a really silly mistake in that I didn't look at the n constraint or the constraint n. So I actually just did it naively, and then I got a time limit exceeded, which cost me 5 minutes. But not a big deal for this problem contest because the rest of the contest was a little bit slow anyway. Okay, this is the one that I was looking for. Okay. But yeah, so basically what I'm doing now is I was just like, oh yeah, let's do the naive algorithm. That seems pretty straightforward. Some of this is because usually for Q2 on the Leetcode, this is straightforward, and you just don't have to think about it, and it is usually right. But I just had a blind spot. There's no way around it. I didn't think about doing this, and then I was like, okay, let's just do it with a, you know, yeah, a little bit indecision on the implementation, but that's pretty much what I do. This is incorrect. It gets time limit exceeded, and as soon as I saw that, I was like, oh, and then I looked at n, which you'll see in a second. But this is just implementing. A little bit slow actually, to be honest, but So I ran it. It looks okay. Let's submit it. But this time I got time limit exceeded, unfortunately. Oh no, time limit exceeded. So I was like, oh, well. I think the first thing I did was I looked at n, and I was like, oh yeah, of course it'll be time limit exceeded. So basically, what I did after that was just create a lookup table that allowed me to remember the last number for a given name. That is surprising. I don't know what I was checking for there. I was just like, oh god, let's just have a lookup table. What are you doing? Don't really. I'm also just double checking on the constraints so that I can make sure that I am able to do what I wanted to do. Yeah, and here I'm just trying to make sure that I'm not getting off by ones and stuff like that. A little bit slow right now, because I think I was just indecisive as to what I wanted. I wasn't sure that this would be good enough, but that's not right. Yeah, I ran the code. I was like, this isn't right, and was a little bit sad. But basically, I just have a typo on line 7. That took a long time to catch. Just one of those days. This was a bit of a hard contest for me. I was like, there's no even S is not even in there, and somehow it never ran. So there must be other issues. Why? When nothing print, I was looking up, and to be honest, I think it was just that something like the auto complete on the thing on the editor got me. Like I don't think that was me, but maybe I'm wrong. Because why would I do that? And then I was like, oh, S is not in there. I run the code. It looked like it finished pretty fast, so I was like, okay, the answer looks good. Let's just submit. Spent about 2 minutes on that silliness. Okay. Q3, avoid fraud in the city. So this one I had trouble with as well. Basically, I thought that I could use some greedy algorithm, and a couple of times a couple of greedy strategies that I did on this one. Neither, a lot of them didn't do that hot. But I thought that I could maybe use a stack to kind of figure out what to clear out by going backwards or something like that. But it didn't really order. Yeah. Didn't really work. I mean, here at this point, I was just proving to myself that that's what I need. I think I knew what I thought I knew what I wanted, but to be honest, I think I was a little bit off when I was in during this. Because at the time, I thought that I could do greedy and then that'll be good. But I was wrong, as the test cases showed me, and I got 3 wrong answers, or 2 wrong answers on this one. But it's a very sloppy contest for me, kind of. And sometimes greedy algorithms are hard to prove. I mean, they're not hard to prove, but they're hard because you have to prove them to a certain degree. And I wasn't able to do this on this one. So what I did was I looked at the examples, and I was not convinced that I was wrong. So that was good enough for me to keep going. Some of that is a little bit on the meta. Q3 is not usually it's usually not hard enough that I needed to do anything tricky. So I just try to do it as the first thing that comes to my mind, which sometimes gets me into trouble, like in this case. But sometimes you have to trust yourself, and today trusting myself wasn't that great, though. But it works. I mean, it's okay. It's part of the learning experience. Some days you trusting yourself will really pay off, and other days, well, you just trust yourself to learn afterwards, I suppose. Yeah, so now I am trying to go backwards and then I thought that by going backwards we just we just fill out the colors as it goes, or sorry, like clear out the rain as we need it. But it was, well, technically it's okay, it was missing an invariant that I didn't really think about, which is that, or the condition that I didn't think about, which violated this invariant, which is that you don't need to clear out a lake unless it gets rained on again. So if something happens only one time, you don't clear it, or you don't need to clear it anyway. You could clear it if you are bored. But I had this really simple stack solution, which is wrong. But what I'm doing now is that basically and I don't know if I need to explain the wrong solution, because if it's wrong, but I thought that you could basically match 0 with the last number that we need to clear, and then kind of go that way, and that's what the stack would give us. but again, it is wrong because I missed that one scenario, a really big scenario where the numbers don't. You don't have to clear numbers that don't exist. Yeah.
I know.
I ran the test cases. It looks okay. Oh, okay. Maybe not the. Maybe not this one. Just forgot to initialize the array. And as soon as it looks okay, I was going to submit. Of course, at this point, I knew that I have to return an empty array, which I didn't do yet, but that's okay. It was just to kind of see where if my approach was okay. It's not, but it passed the example cases. That's why I was able to write the second half, which I reuse anyway. So it's not a loss. But of course, if it was not right at all, then I would not have approached it yet. Oh yeah, and I also just forgot the API a little bit for set for remove. That's it doesn't happen that often that I need to remove maybe. Basically, this is just a very naive algorithm. Basically, given an answer that I came up with, we just see if it's in the set. If it's not, then we add it. If it's already there, that means that's not possible. Otherwise, we remove it when we need to remove it. And that's pretty much it. That the answer, and it's right answer for the inputs, but it's wrong, as we'll find out. But I was ready to submit. And I got wrong answer. I was like, oh no. Why is this wrong? So this is wrong because the second two, we tried to print, we tried to clear the day for the second two, but we don't need to clear the day for the second two because, oh sorry, before the second two because, well, it's not set yet. So that's what I thought was my mistake. So I try to fix that, which is true because you cannot clear a lake before you fill it. I mean, you can, but it's right. So that's kind of the strategy here. Right now, I'm just thinking about how to go about implementing this. But yeah, I just go, okay, if the number is done, we don't have to push it. That's basically my attempt to solve this or fix the bug. Because I was like, okay, if you look at it in order, the first two, well, you don't clear it before you serve the first two because it's unnecessary. So that's basically what I'm thinking of here. Apparently I really took my time here, but oh well.
Okay.
But yeah, now what I was trying to do to kind of fix this by hacking is by looking at adjacent values. Oh, sorry, we keep track of the counts, and then if we get to 0, then we're good. I thought I had to start over, but then I was like, oh, maybe I can just hack what I already have, actually. Unless I misremembered. This is roughly right. I just need to handle one case. Yeah, I basically just go, okay, if the count is positive, or sorry, if there's 0 left in the count, then we just don't pop it, and we also keep track of the count as we pop stuff. Yeah, and the answer looks good. I was like, yeah, okay, let's submit this. I think I was a little bit YOLO on this one because, to be honest, even then I was not very confident. Oh, you have to move this back up, but I think some of it was that I expected Q3 to be slightly easier, so I was like getting a wrong answer. Oh no! Oh no, I was just running the code, not yet. But I do get a wrong answer, so spoiler alert. I was like, okay, that's a little sad. Use my debug print statement to kind of see. But yeah, the reason was basically I tried to clear 1 first.
To be a 2 first,
and so that was not good enough. We
enough.
wanted to clear.
It has to.
We want to clear.
Up next.
Sorry, we cleared them in the wrong order between the 1 and the 2.
Oh.
So that's kind of why
a lot of people got this wrong. So
yeah, and I clicked the refresh button, and I was like, wow, a lot of people failed this, and only 35 people got it right so far. So I knew that I was not fast, but not like I was in good. Like I just to kind of get a gauge of the difficulty a little bit and try to think, is there a dumber way that I can think about this, or am I missing something obvious? At this point, I was just convinced that I'm being dumb, and that I needed to kind of start from scratch, if you will, because I basically reformulated or kind of go with the explanation or the really kind of ask myself what problem am I trying to solve with this problem, and it is that for each 0 we want to get the next index that's coming up that's clear. So what I end up doing was using a heap. And basically what I do now is for each lake that appears, I put it in a hash table of lists so that we could kind of keep track of all the indexes in which it happens. And now that we look at each key, I was trying to think about when to put items into the heap. That's basically what I'm doing at this moment. I was like, okay, you only want to put items in the heap if there's at least one entry, right? And I was like, is that really the way to add this? It's a min heap, okay. And also that it is a min heap in Python, which is not common. But yeah, and I was like, I don't need to relax it yet. So what I'm going to do now is, if it rained on a certain number or lake, well, if it's not cleared, then we return the because then we haven't cleared it. Otherwise, we put it into the set, we mark it as being rained on, and then we try to find the next time that index comes up. If that index doesn't come up, then we don't push it to the heap. But if it does come up, we take the next element that is bigger than this index and then put it in the heap. And the idea being that when we take things out of the heap, we always get, because we're sorting by the index, we always get the next element out of the heap. Or sorry, yeah, the next upcoming element, the one that comes up the soonest from the heap. And basically this is what I do. And going through the lookup array, I just go, okay, if the index is, that means we just remove stuff that we already like don't have to consider because it's in the past. And then we look at the first index after that and then put it inside the heap. And then now when we need to take things out of the heap, meaning when we have a 0 and we try to figure out which one to clear, we just take the top because that is the item that is the closest to you, that's coming up the soonest. And that's what I do. And then later on, I just double check that we remove the right one, or that it is possible to implement this solution. Yeah, and we only take the first element if the heap has at least one element. Otherwise, we just I put one, but you could really put any number. It's just a placeholder because it doesn't matter what you have because it doesn't affect the output in either case. And to be honest, right now, I was a little bit doubtful that I was getting it right because when you already have 2 wrong answers, your third one, I was trying to be like, okay, let me think about it a little bit first. And then I submitted it. And I got accepted. Yay! I was very thankful and very, really happy that happened. But cool. Q4, find critical and pseudo-critical edges in minimum spanning tree. So this is a really hard problem, really tricky problem, for me anyway. It required learning about minimum spanning trees, and I actually did this a little bit harder than it needs to be, but yeah. But yeah, at this point, to be honest, I was just drawing a lot of stuff on a notepad to kind of just try to figure it out. The idea behind this is that I recognize that so minimum spanning tree is a standard, quote unquote standard, greedy algorithm by itself. Not that I had to prove it, but I was trying to figure out a case where greedy maybe is not good, and I was just trying to figure that out. But after that, yeah. Otherwise, I was just looking at the sample example cases and trying to understand a little bit. I think at this point I was a little bit incorrect in that I thought that the pseudo critical edges are only the last ones you add. But that's why I was playing around and trying to prove to myself. But thankfully, there were a couple of couple of test cases where that already isn't true. But yeah. So I am gonna skip a little bit ahead because I really just was trying to do proofs on my notepad and book for a long while. Um, Feel free to stay, but I'll have a link below so you could jump along with me. But yeah, cool. Not sure I'm going to finish this one. That is entry. Welcome back. Yeah, so basically now I've settled on, I basically proved to myself that Cusco is good enough. And now I'm trying to find the critical mat, just trying to play around with it a little bit by trying to solve it. And with Cusco, you know that you're going to have to do union find, and that's essentially what I start off here. And this is just standard union find. I don't know if I recommend, doing it my way, but just, play around with how you would do it. Yeah, so far still standard union find techniques. And because the edge weight could go from 1 to 1,000, I was just a little bit lazy to do the sorting. It's probably roughly the same, really, but because they're only given at most 200 edges. But right now I'm missing one condition still. I just thought I could start playing around with the Cuscos and then kind of see, like, help me visualize it a little bit. Yeah, this is very basic Cruise algorithm for calculating union find. And basically what I'm saying is if we process all these edges and we got one component, then we're done. Again, at this point, I was under the mistaken assumption that only the last edges that you process will be maybe, and the rest are on the must. And for must, I mean that you have to have them, meaning that they're critical. Maybe meaning that it's pseudo-critical in the definition of this problem. So this is wrong, but my assumption here at this point was that, okay, if this is done now, let's look at all the edges that we just add in. And then, yeah. And then now I notice that I need an index, so I'm just looking up where to put the index. I'm okay, just put on the edge. I didn't want to spend time looking up combining them, so that's why I did it this way. It's a little bit awkward for Python, but you could ignore that probably. So this is my first attempt. Again, I was wrong on this one, but yeah, now I'm just clearing up some syntax errors. The way that I write that is because that's the way I write it in C++, and that works in C++. So I was had to fix that. Oh yeah, and I wanted to make sure that my scope is right, so I did that. But I also, this is just cleaning up, changing my union find to be based off different inputs. Usually, my experience is that you only need one union find things, but in this case I was not. True. Really? So here I got an answer. It is not right for the second case, I think. I know this is right, but I'm still trying to think, trying to prove the greedy wrong, because I'm still not convinced at this point. But I do get the right answer, and I can't really prove it wrong, so. let's see what Larry does here. So the case that I was trying to figure out is that and that I'm trying to think about how to handle it is I thought that there may be a case where when you add an edge that you don't that it might not be necessary. Basically there are edges that right now I'm rethinking my initial thought that you can only add every edge that is before the last series of edges are definitely critical edges. So I was looking at I was thinking about it. I was like, that doesn't seem right. So that's what I'm trying to write code to get about. I do implement this a little bit incorrectly. Because basically what I was trying to do is say that, okay, like if, and this is for the ones that before the last one, even though that's wrong as well, but I think I was thinking about it now. But basically, let's say you have a triangle with a string on it, right? So like 1, 2, 2, something like that. Triangle with a string on it. Then in that case, you definitely don't need all 3 of those edges, right? So that's what I'm trying to implement, but incorrectly. Well, yeah, because I assumed that in that case they all have the same parent. So basically, I do a dedupe by the two components that they add, but that's not sufficient because multiple components can be added to the same component at the same time. So that's kind of the trouble that I was handling with. Though I think I do submit on this one. But that's basically what I'm trying to solve in this part of it. Okay. Well, fail fast, I guess. Huh. Did I mix them up? No, that's not true. But yeah, but I did get a wrong answer, so I was like, okay, it's fine. I did submit it. I wasn't super confident about it, so I was just like, okay, now we have an answer that we can think about, and that is the triangle case that we talked about. So I think before that I was considering only like a circular case, I suppose, but yeah. And now back to trying to figure out how to do this. But basically, at this point, I still end up spending another half an hour on this. But I knew that half an hour. So there are a couple of components of things that I want to say. One is that looking at now I know the output and the outcome. That I definitely did it in a way that was more complicated than necessary. Basically, I did it in read times z log e or something like that, where you could do it in read times e squared. But in any case, from here, what I thought I needed
Oh, this
is
the last number.
cycle finding. And it's an algorithm that is not
Hopefully
that
it
hard.
works.
It's not that easy either, but it's not impossible, which is why I grind. But that said, it is an algorithm that if you had practiced, it's really okay.
This is not true. Okay.
But if you're out of shape, as I was, it would take a while. But you actually did not need to know that algorithm. You could have just did a more brute force algorithm in constructing the tree, and that would have been fast enough. But I did not know that at the time. Cool. So again, I'm going to jump a little bit forward to that. So stay with me. There'll be a link below. Thank you. So we don't handle the transitive part very well. I think I have to do a depth first search with back edges or something like that, but This was not true. So. Welcome back. So at this point, I knew that what I wanted was I need to find a cycle. Yeah, I needed to find a cycle slash. Well, I actually did the critical path, which is that if, and this is very fun, computer sciencey. But I was using depth first search and back edges to go, okay, if this edge allows me to reach earlier than I have, that means that this edge is, wait, if this edge does not allow me to go back to earlier place with a back edge, then that means that there's no cycle containing this edge. And that's kind of the algorithm that I end up trying to implement, and it took a long time, but yeah. And you do that with a depth first search, so the entire complexity is relatively fast. But it turns out that you don't need it for this algorithm, for this problem, given the constraints. But I did it anyway, so that's why it took a while. Otherwise, I probably could have gotten it nowish if I had just kept on coding on the more naive way. And the more naive way is just running the minimum spanning tree and seeing whether it is connected the same way. And basically, at this point, I converted the graph into an alternative graph that has the original graph, but using union find. And if you think about Costco, it's just about, and union find in general, you have two nodes, you combine them into essentially one super node. And that's basically the idea that I have here in reconstructing the edges. And basically now I'm given these edges that we constructed, I just recreated a new problem with all these edges. And then I go, okay, let's try to run a depth first search to calculate the trees. And this is,
how to write.
for now, this is very standard depth first search with cycle finding is, it's just basically given a node and a parent, and you don't go up the parent. I do make modifications here later on, as we'll point out. But again, I am actually very rusty with this algorithm, so that's basically what I'm trying to do here. And this idea of back edges comes up on critical edges and other similar recursive tree algorithms. But that said, I don't know if I recommend needing this. It's just that once in a while you need it. It's very rare for an interview. Or at least it's very rare that you need both these things on an interview in one problem. But too rusty on this one. But yeah, right now I think I was just trying to look through some old code on my computer just to make sure that I get the just make sure that I get the parameters correct. So I had to pass in the edges. I forget. I mean, at this point, I was just forgetting whether like some of the initial edge case or edge conditions or base conditions. This becomes n squared. And I was a little divided between. I was still a little bit tired, but I was a little bit divided between doing it by using effectively a global versus passing it in. Normally, I would probably do it in a global, but I wanted to pass it in because I wasn't as familiar as I used to be. So then I don't have to deal with, and also because I called this multiple times, I don't have to worry about scoping and clearing out the data and stuff like that. And again, I have to put back the index. But yeah, basically now I'm just thinking through a little bit how to go through it. I think right now I was just thinking a little bit about how to deal with the parents in a because in this case in the supernode we have multi-edges that are not as as it's not a there are multi-edges which in some cases they're not, so or usually they do not need it, but this is not necessary. No, it's fine. And again, I'm falling because the code that I was referencing, to be honest, is in C++ because I wrote it a long time ago. So that's why some of my syntaxes feel very C++y and less Pythonic. But yeah, all of what I'm writing is a basic part of those back edges recursive tree algorithms. The one that I remember is the critical edge one. So yeah, so definitely look that up. It's kind of hard to figure out what's in scope for an explanation. So maybe I'll do another video on that in the future. But yeah, now I just have a step in type variable. And then now I'm able to start on my recursion, I think. Yeah, I have to put in the wizard away. And then just set the step and the back edge up to the current time step. I forgot to increment it here, so I do later go back to fix this, but and this is just the x is equal to parent so that we don't go down to your parent, but we actually need to change that a little bit of a spoiler. But yeah, if we already visited, then we just this is pretty straightforward. We set the current node's back edge is equal to the earliest step either here or the time in which the time in of whatever you want to go, because that's already set up. Otherwise you just go to that step. So there's a lot of debugging after this, which is why I wanted to commentary or add commentary to this part, is so that I feel like learning how to debug is a really important skill and happens in real life more than anything. So yeah. And now otherwise go to you do a depth first search and then you calculate the you get the min of either your current node or basically it tries to go, you trying to calculate the farthest that you can go back in time. And if oh, you gotta be kidding me. Yeah, I'm just trying to look at the indexes, but if you are not able to, or if you are not able to, I can't see, but and now I'm just setting up the answer, which is that in the numbers, once we get the cycle, then we do stuff, right? We go, okay. That means that we have to add this edge into the answer. If the answer is that is I did a little bit weird, but yeah, I have a typo on else, I think. Yeah. But basically, after I run the depth first search or the get cycles, it should tell me whether an edge should be in maybe or should be in must, and then we just at the end, if it's done, then we return it. So now, just fixing a lot of syntax errors because, like I said, I guess my years of C++ kind of sipping a little bit, and I look at the answer, I'm like, okay, that's not right at all, right? I'm like, oh no, and to be honest, this is way this is where practice makes perfect, which is that if you are confident about your algorithm, then you know that's your implementation. And if you're confident about your implementation, then you may second guess your algorithm, right? In this case, I was not sure about my algorithm or my implementation, which makes this a little bit harder because I wasn't sure that like maybe I implemented correctly, but I just didn't, like the algorithm just didn't work, right? So the first thing I noticed is that you actually need to not just the parent, like it's okay to go back to your parent, but not your parent, just not the same edge, because it could have multiple edges, right? So that's kind of why I add that if statement, and then that looks roughly the same, to be honest. But I knew that that was at least a correct way to handle it, so I was okay with that. In that, like, I needed that fix anyway. And at this point, we're running pretty low on time. We have about 10 minutes left in the contest. And yeah. This way. And yeah, I realized that I got the nodes backwards, which is that actually I want if the back edge, if the edge back edge is before the current time, meaning that using this edge allows me to go back before then that means that there's a cycle, or the other way around. Yeah. So then now that means that this edge is critical because, oh sorry, if you're not able to go to a time before you first process this this node, that means that there is a critical edge and that it is not part of a cycle. So that's kind of the thing that I fixed. I just fixed the variable names, but there was also one more bug, at least one more bug. And some of this is just a little bit out of practice because I think I mixed up the definition of what to put in and what to not put in or what makes it critical and what's not. And I've accidentally put the edges that would have been part of a cycle on the not critical one. I forgot to increment by 1, so that's 1 to code. And yeah, I just have to non-local. And then as soon as I do that, wait, I meant non-local, so that's 1 it again. And then I got roughly the right answers, but not in the same place. So I was like, that's not right. Like the thing with debugging this one is that we're straight up missing edges that I know that we're processing. So I was trying to figure out why that is the case. And I do remember why, which is a little bit sad, but it's because I was a little bit hasty in implementing. So I printed out. I was like, okay, there is stuff in here. So what is going on? Unlike earlier.
Backwards.
And the short story is because, yeah, here I knew that I had them in the wrong order. That's fine. So I had them in the right order, but I'm still missing edges. And the reason is because the way that I did it, because I have the if statement a little bit too early, because we do the check and the union step at the same time. So not all it doesn't all come out at the same time. And you kind of see me fix this real quick. So, but yeah, but that's kind of me on this contest. It was way interesting. I liked it. Let me know what you think about it as well. And I will hang out with the other Larry, see if we can spot his bug. But when you see it, you'll see it. Anyway, I'll see y'all. Hang out with the other Larry in a bit.
Right.
And join the Discord channel.
Union it again. Oh my.
Why not? We have 5 minutes left. I mean, I know maybe I celebrated too much on that one, but that's a hard problem. I didn't expect to get it, to be honest, and there's only 5 minutes left. People got it really quickly. Oh my god. Whoo! Alright. I know I usually do the problem review live. But that was a long contest, so I'm going to take a quick break. You're not going to see it, but just that, you know, usually I film everything live so that you see everything. But you saw the coding. I'm going to take a few minutes and then I'm going to record the rest because, as you can see, that was kind of tiring. Okay, you don't actually have to wait. But yeah, so I think just as a recap, as a retro, kind of try to figure out how I can learn from this problem. Problem set. I thought I did okay on Q1, Q2. That was a silly mistake. I just didn't read the constraints, and it would have been clear that I should have done it in linear time. So that's 45 minutes that I gave away. Q3, I probably could have been more thorough in my testing. That was a little bit unfortunate. And as soon as I think some of it was that I just really thought that it would be easier. Maybe too much meta guessing versus just solving the problem. And once I kind of reset myself mentally and focused on solving the problem, I got in about 6 minutes, which is not fast, but not that, you know, it's okay. It's just that, you know, by then I spent 15 minutes on incorrect solutions plus the 2 penalties, so 25 minutes total. Q4, it turns out that there was a simpler algorithm in the sense that you could do the constraints makes it so that you could do a more naive algorithm. I don't regret practicing something that it's been a while since I practiced it, so maybe next time I'll be fast in either case. But yeah, maybe I could have done it more naive and it would have saved me 20 minutes and maybe a penalty or something like that. But overall, it's still not, you know, I don't think it would have moved the ranking that much because everyone is cluttered in the same place. Maybe I could finish. Maybe I would have been top 50, but you know, that's okay. I focus on the learning and I feel like I learned a bit on this contest. So that's all you can ask for, I think. So anyway, that's all I have. I know that I record this video in a weird order, so you may have heard me say goodbye a few times, but this time it'll actually be true. Have a good night. Hope you know you have a good week, and I'll see y'all in the next video. Bye bye.